this. Now, can such kind of behavior come out as a solution of a deterministic differential equation? The answer is yes. Okay, depends on what E is, okay. But not most of the time. Because in order to see the existence and uniqueness of the solution of this problem, we know that our B should satisfy some assumptions. In other words, this vector field should be at least smooth, and its components must be smooth. And if the components are smooth, you expect B to be smooth as well. You are already assuming that, already assuming the smoothness. So as a result, you are getting, a pretty regular, pretty smooth trajectory. Okay. But in order to model such kind of a thing, you not only need, such kind of an evolution of x(t), x of 0, x naught. Okay. And E is the same. But you have to incorporate some kind of randomness. In other words, you have to incorporate some kind of noise. Noise is the thing that is responsible for the randomness. Okay. But what is noise? So noise is a random thing, something has such a bumpy behavior. So if this is random, the sum would be random. And hence, in other words, if this is bumpy, then roughly the sum is bumpy. And hence, this derivative should represent something bumpy. There was a lot of kinks. But the question is, can Newtonian calculus deal with the kinks? The answer is no. Think about, so what is the most elementary example that is, not differentiable? So take absolute calculus. So once you have a kink at a point, okay, your calculus breaks down there. The Newtonian calculus breaks down. What if you have a phenomenon where you have kink at each and every single instant actually? So how does this calculus can work in such kind of a situation? So if you want to meet with the real data, okay, you not only have to, introduce noise into thing, because this noise is a monster, it's going to basically, swallow this calculus, okay, or this, classical Newtonian calculus cannot hold the weight of, what do you call this randomness and noise. So what you need to do, you have to think about something else. Are you getting the point? You have to think about something else. Now, if I, for example, let's give this noise a particular form. Okay, a particular form that this noise has is something like this. Okay? Something like this. So maybe I'm replacing noise by some b of x of t, okay, times xi of t. Okay. So this xi of t is basically what you call the real randomness. Okay, that's randomness. And this is just a coefficient of it. Are you getting the point? Now, in other words, currently in its current form, this expression or this entire system doesn't make sense at all, because it's going to suffer with this problem actually. So if you don't have a smooth drive, how you can have differentiability at the K side? So in order to really make sense of this, what we need to understand first. So first, the first thing should be to understand noise. What the heck this noise is? Or what the heck this xi of t is, if I assume p of x to be something deterministic. B is the m by n matrix. Okay. M by n matrix and xi is a n by 1 matter. Something like that. Are you getting the point? So what you need to do, the first thing should be to make sense of the noise. Okay? To make sense of what you call this randomness. What should be the second thing? So let's try to formulate some questions that can help us to basically make sense of this phenomenon. This random phenomenon. So the first thing I need to know, I need to rigorously define what we mean by a random process or what we mean by a noise. So the first thing that we need to define, you must define, in order to make, if you want to make sense of this equation, okay, I need to define what you call this noise. Okay, or this xi of t. Okay, that's the first thing. The second thing that we need to define is that what is the meaning of having the solution of this differential equation? What is the meaning of having x that satisfies this differential equation? Okay. Now, how we can find this differential equation? Are this x or the solution of this differential equation involving randomness are driven by the randomness? How do we solve such kind of a differential equation? So how do we do it? How do we solve, for example, this equation? So we need to just integrate both sides. And that integral expression is going to be, we can roughly say that it's a solution of this differential equation. So how about this one? Let's try to do something similar. So if we have this, let's need to define what is the solution. And obviously, if you have a solution, I need to talk about the properties of the solution. Talk about the properties of solutions. What do you mean by properties of solution? It's say existence and uniqueness. For example, it's long time behavior. Okay, maybe stability, as I said. Many different things. In other words, all those questions that you ask in deterministic sense. Okay. So let's try to have some sense of meaning of the solution for this differential equation. So what could be the potential meaning for this differential equation? Formally, if I say that this xi of t, okay, so if you want to give a meaning to the solution, is a derivative of some kind of randomness. Okay. Now this is itself a very troublemaking thing because this is random, having a lot of things. What is the meaning of having derivative of it? So you have to first deal with this monster as well. But imagine formally that we say that xi of t is the derivative of something else. And then if I multiply, for example, dt, multiply dt from the both sides of the equation, so you're going to get x of t equal to what? v of x of t dt plus if xi is, so it's going to be v of x of t and tw of t. So we're going to have something like this. Okay, because if the xi is t by dt, and roughly you are multiplying dt by x. Both sides will get this. So in other words, you have to write the equation into its differential forms. Okay, so that's what we do here. We take the dt on the other side and integrate. So we're going to get x. Then so we kind of took the dt on the other side and integrate. So when you're going to integrate, what are you going to have? So you're going to have x of t equal to initial condition plus the integral, say from 0 to t of this b of x of s ds, okay, plus the integral from 0 to t, say b of x of s and d of s. Roughly, this what should be the meaning of the solution of a differential equation driven by some kind of noise. This could be. Now, what would be the immediate questions on such kind of an expression? I know x naught. I know this guy. Should be. So I know this guy as well. What is this guy? That's a Riemann integral. Okay? Or at worst, it's kind of Riemann integral. We know what is this object. Okay? Because you have something deterministic and you are integrating it with system. Okay? You are integrating vector field with respect. We know how to do it. Okay? The real monster is this. What is the meaning of integrating with respect to differential of some randomness? So the first thing is, what will be the meaning of differential of randomness? And the first thing will be, what is the meaning of randomness process, a random process? Second, what would be the meaning of having the differential of a random process? Third, what would be the meaning of integrating something with respect to the random process? So we need to have to define all these things actually. And this course is all about, so what we want to do is that at the end of this course, we must be able to understand this last line. That's what we are having. We must be able to understand this last line. Not just understand, but very rigorously understand actually. So the rigor is going to be. And this says all actually. This description says all. So what we want to do? We want to understand noise first. So we want to understand what is the random process. What is basically the key contents of this course. The key contents of this course.
कैपिटल बी और वो जो आप एग्जैक्ट ये दोनों को लिखा हुआ है इनको फिर से
So B is something, some expression. So it's a matrix actually. Okay. And its dimension is in such a way that this becomes basically a vector n dimension. So it should be what? N by m. And this must be n by 1 matrix, so that we can have n by 1. That's n by 1 vector, n by 1 vector plus n by 1 vector. So this B is a matrix depending on x of. Okay. In other words, if you take n equal to 1, that's something in one dimension. But at the moment, it is not representing just like this is not just a differential equation. This represents a system of differential equations. Right. Okay, so what we want to do? So what is our key targets that we would like to achieve with this. So the key targets are this. In other words, the key contents of this course are. So we'll begin with developing a theory of random processes. Okay. Random or stochastic processes. Okay. The theory of noise. What do we mean by noise? How does it behave? What it is actually? What do you mean by noise? That's what stochastic processes. The next thing that we would like to do is going to be, once you have the stochastic process, I'll talk about one particular example. So we will be, all these stochastic, for this theory of stochastic process, so one of the key examples that we will be interested in is going to be something called Brownian motion. Brownian motion is going to be the concrete example illustrate many of parts of this theory and things actually. In other words, we will be interested in kind of differential equations driven by noise. That noise is Brownian motion. Okay, the Brownian motion is an example of stochastic process. The analytic process. Brownian motion is going to be our key process. It's also called Wiener processes. Wiener process. And we'll go in detail of its properties. So in other words, we have the theory of random processes. We have one concrete example of random process that we are interested in, and then we'll talk about what is the meaning of having the differential of the Wiener process are in this stochastic process. In other words, we will do something what we call eco-calculus. Okay. The calculus of stochastic processes. That is the next thing that we like to do. It's how to differentiate them, how to integrate them, what is their theory. And the last part of the course, as suggested, we would like to deal with such kind of stochastic differential equations. Okay? SDEs. So we want to move from differential equation to stochastic equations, where the differential equation is driven by the noise of Brownian type of Wiener process. Okay. Now, as we have our experience with Newtonian calculus, actually, that you can learn maybe limits and maybe define limits and computation of limits in 2 days, and maybe differentiation in 2 days, and integration in 2 days, and then maybe go back and integration, the calculus. Okay. But if you want to justify that theory of integration, we did a course what we call the real analysis. We not only just understood how to do the computations of in calculus, but we kind of justified that why those computations are valid actually, or the rules that we did are wrong. So you can ask a question here. Are we going to do the computational stochastic calculus? The answer is we can do it in 2 hours or maybe 4 hours. Okay. Just one lecture is enough to do the computations of a stochastic calculus and learn it like that. The real thing is to justify. So this is going to be kind of real analysis for the stochastic calculus actually. So we'll try to justify every single thing in detail. And hence also do when we talk about computation. So it's going to be a rigorous course. So it's not just going to be a course on doing primary computations. Computations are easy. Okay? Because we know the Galen series to come up with the formulas, which can allow to deal with such kind of differential equations. What we want to do, you can very good. Okay. Are we happy with this? Let's ask a new set of questions. Let's ask a new set of questions. This new set of questions is are you realizing that what you are doing is we are changing the foundations of the calculus. We are coming up with a new kind of a calculus. Okay? And once you have this, what immediately you can do, so everything that was kind of depending on the Newtonian calculus, you can think of doing the stochastic version of it, or you can think of generalizing it, okay, to the stochastic version. So, you learned, for example, a lot of insurance model in your actuarial mathematics course, but almost all of the models that you learned there were deterministic actually. So they were deterministic formulas. We have the insurance models, which are stochastic. You have classical mechanics, for example, did Lagrangian mechanics, classical mechanics, okay, and you did basically some kind of calculus of variations to understand. You use this Newtonian calculus to do what do you call this Lagrangian mechanics or classical mechanics. So you can say that can we do stochastic stochastic Lagrangian mechanics? Yes, you can take all of those tools which were previously studied in deterministic manner, you can take them. This is stochastic generalization. So this is generalization. Why I am calling it generalization? Because think about it. If you have a complete theory of doing this stuff, how can I get this deterministic theory out of this theory?
Nice.
Just take noise equal to 0. And the same theory will start giving you the answers here. Same or similar. That's a big claim, but roughly, if you get rid of the noise, you have the deterministic theory. So it's a pretty exciting subject. So what I would like to do in the next part of this discussion, obviously, we will start talking about the noise from the next week, and we will start with some of the fields in today class. In solving such an equation, one of the key problems is this integral. So you have one function and you want to integrate it with respect to another kind of function. Okay? So if I give you the liberty to define this integral for me using your previous knowledge, what would be the most appropriate notion that can help you to define such kind of integral? Have you? Riemann-Stieltjes is the one of the key candidates, because there you learned actually that how to integrate one function with respect to other functions. In other words, randomness is randomness, but it's a kind of a function actually. So you have to integrate one kind of function with respect to another kind of function. So in other words, okay, can we, so if we have, this theory of Riemann-Stieltjes integral, why we need a new theory of integration? Because I want to show that this theory of Riemann-Stieltjes integral is very limited. It's very limited. It doesn't give the answer. It can't even deal with the deterministic functions. Actually, you forget about random functions, random processes. So let me just convince you that Riemann-Stieltjes integration is good, but it's not good enough. Okay? So let's convince ourselves. Please. So let's quickly recall the way we defined Riemann integrals previously. So we said that imagine you have an interval, okay, and you split this interval into, and you have a function defined over this interval, okay, and you split this interval into n parts, x2 and so on and so forth, or x and bn, okay. Then if I denote, for example, okay, by delta n, this mash actually, okay, let's agree with the notation of the book. We're not calling it x naught, calling it p naught, which is fine. It doesn't matter. Whatever name you want to give, you can give actually. Then what would be the meaning of integrating a given function f, okay, that is bounded, okay, over the interval a to b? Okay. So we may define it in several ways, but one of the ways that we can do is that, okay, you have this, what do you call this, interval a to b, and you have this curve, so you split your this interval into, what do you say, parts, draw the boxes, and then try to approximate the area of, under this curve through these boxes. Okay. So in other words, what you need to do, you have to evaluate f at the point, for example, tau I, where tau I is a point between any point, maybe suitably chosen point between the interval ti minus 1 to ti. Okay, so we know that sometimes we take tau to be left hand point and right hand point. We take it to the middle point. We take it to be, the maximum of, the value of the function. The point where the function takes the maximum value on this entire interval, so you can define it in a pretty simple way. So compute the value of the function at a point in the interval ti minus 1 and multiply it with the width of the interval. So that becomes what you call the area of one rectangle. Okay, and then sum it up. Sum it up from I equal to 1 to n, okay? And what you need to do, you have to, increase the number of the intervals actually. In other words, we know that the more intervals you have, the more better approximation you're going to get, by these rectangles of this area under the curve f actually. Okay? So in other words, so if this limit, which I call limit norm delta n, goes to 0, okay, What is norm delta n? Norm delta n, okay, is the maximum of Ti minus 1, where I runs from 1 to n. In other words, so out of all these subintervals, lengths of the subinterval, take the maximum one and turn it into the 0. So if the biggest subinterval, you are turning it to the 0, so each of the subinterval will turn it to 0. Now when